Chapter 3, what mechanism produces the logistic S-curve? We're going to take an arithmetic look at what happens when we have logistic growth. Suppose we have 10 people, K is equal to 10, that's the maximum infectable population. And suppose we introduce one infection. We have one infection, there are 9 not infected, and of course they are susceptible. And of course, this one person can affect any of these 9, and then we would have eventually 2 infected, 3 infected, 4 infected, all the way down to full infection. And of course, the susceptible number decreases. You could add 1 and 9 is 10, 4 and 6 is 10, 7 and 3 is 10. We always have 10 people here total. The person is either infected or susceptible. There's no one hiding off in the closet, so to speak. The number of interactions between these two is what governs the growth, the rate of growth. 1 times 9 is 9. There's 9 ways in which it can spread. This one person can infect any of these 9. If we have 2 people can affect any of these 8. 2 times 8 is 16. And you can continue 21, 24, 25, 24, 21, 16, and 9. And then I didn't put a 0 here. Since the rate of change is proportional to the number of possible interactions, there's a proportionality constant. I said, let's just assume C is 0.01. I just made that number up. It's easy. You can just multiply 9 times 0.01, 0.09, 16 times 0.01, 0.16, and on down that column. It turns out this logistic growth constant is equal to C times K. If you want to find out why, you have to take a course called differential equations. For now, we'll just accept it because this is pre-calculus. This would give us infections per day. Number of infections per day, that would be the unit. Now, if you take the reciprocal on a calculator, you can use the 1 over x key. 1 divided by 0.09 is about 11.1 days per infection. 0.16, you can use the 1 divided by x key again. You get 6.3 days per infection. And of course, in here in the middle, 0.25, reciprocal is 4, and then it stretches out again. This is what gives you logistic growth. It takes a long time in the beginning. It's kind of progressing slowly. Then it speeds up. Right here, it's raging. Okay, there's the maximum infection rate. And then it slows down again. It levels off, so to speak. We can calculate the total time here, 11.1 seconds, add 6.3, 17.4, add 4.8, 22.2, et cetera, and 56.8 days to total infection. And that's when the whole population would be infected. Woohoo, we reached a milestone. Just to recall, this is the equation, K over this big mess. And if you were to plot this, you could take all these parameters, take this 0.01, multiply by 10, use RL would be 0.1. You plug a 0.1 in here. K is 10, I0 is 1. Plug it in, get the equation, and put it into a graphing calculator, for instance. You'd have this nice smooth S-curve. You can do that if you're ambitious. If you superimpose upon that these data points, you'd have to do time versus infections. So you plug in 0, 1, 11.1, 2, 17.4, 3, et cetera, plot these data points. It follows this curve. It actually undershoots it here and it overshoots it here. And that's because we're doing a discrete approximation of this continuous function here. We could fit this curve better. There's a couple different things we can do you learn about in calculus. You could make this discrete step from 1 to 2 smaller. You could go 1, 1.52, 2.53, et cetera. If that didn't suit you, you could do 1, 1.1, 1.2, 1.3, 1.4, and then you could use the increment of 0.01, 0.001, and the discrete model would approach this continuous model. This curve is continuous, the points are a discrete model. And I have full infection at 56.8 days, that point right there. So what we've done here, believe it or not, this is a very clever way of solving something numerically called an autonomous differential equation. It's a very clever way I came up with. Got the wrong variable there. Okay, if you take differential equations, that's a couple semesters away. This is what's called an autonomous differential equation. We won't get into that definition, but you can start with this and produce this equation. That's solving the differential equation. You have to assume some initial conditions and the like, initial or boundary conditions, but you can use that to produce this. You can derive that equation. We came up with a numerical way to approximate it. That's a big area of differential equations, by the way. This also gives you some insight into how the SIR model is going to be constructed for us. Here, everybody is either susceptible or infected. So you can call this the SI model. All we have to do is add the R. When we get to chapter 11, we'll follow the same format, except for, and we have a slightly different way of working this out. We don't solve it as an autonomous differential equation. We'll vary time instead of infections. But every time period, what we'll do is we'll siphon off a certain number of infected that are recovered. So we'll add one column essentially, and it will give us the SIR model. So this is providing a very valuable precursor for understanding the SIR model. So the SI model, once infected, always infected, not good for virus spread. When you get a virus, generally you recover through whatever means. Good for some bacterial infections. It would actually work perfectly fine for a zombie apocalypse. So if you're into that sort of thing, I live near Niagara Falls, which I've been told could be an epicenter for a zombie apocalypse. So I may have to pull this out at some time in the future. So, okay, that's all for this video. Been a pleasure.